Hello again. Today I want to talk about thermonuclear fusion. This is a nuclear process that occurs inside the Sun and other stars, and it's the process that produces energy in the Sun, and it's of course the Sun that powers almost everything on the Earth, including us and the weather and just about everything that happens on the Earth. So it's an important energy source for us, and this is the process that produces that energy. It's called thermonuclear fusion because thermo meaning heat. It's caused by the high temperatures in the core of the Sun. Nuclear because it involves atomic nuclei. Fusion because that means two things are bonding together, right? So it's nuclei fusing together into larger nuclei, and that's driven by heat. Now I show the periodic table on this first slide because the elements of the periodic table, turns out they're formed by thermonuclear fusion. The reason we have iron nuclei and the heavier nuclei with many particles in them is because they're fused together inside stars. That is where the elements actually come from. So not only is it important for powering the solar system, but we couldn't exist at all were it not for the elements being formed by thermonuclear fusion. Now, to understand the process of fusion inside the Sun, we can go back to these two fundamental forces of nature, the EM force and the strong nuclear force. You know that the EM force is attractive between electrons and protons, right? But it's repulsive between electrons, repulsive between protons. But it's the attractiveness of electrons and protons that cause atoms to exist. It's why electrons sit in their orbitals on atoms, and it's also what bonds atoms together into molecules, and it's also what drives chemical reactions. So we are creatures that are composites of millions and millions of atoms. Those are held together by the EM force, and we're basically chemical creatures. There's many chemical reactions going on in us. Those are driven by the EM force. So this is a very important force in the way we function as physical beings. The strong nuclear force is what holds atomic nuclei together, right? It is attractive between protons, attractive between neutrons, and attractive between protons and neutrons. So this is why atomic nuclei are held together, even though protons are repelling each other in nuclei via the EM force. So now the thing about this force is it's got an extremely short range, right? Even if two nucleons, protons and neutrons, even if they're on opposite sides of the nucleus, they won't even feel this force. They have to be extremely close together. If you understand these properties of these two forces, you can get a basic idea of why thermonuclear fusion occurs inside the Sun. So in the Sun, let's say these are protons. The Sun's mass is mostly protons because hydrogen's the most abundant element in the Sun by far, and in the high temperatures in the middle of the Sun, the atoms don't exist. The electrons are not bound to the protons. They're just zipping around by themselves. So you have a lot of protons moving around at very high speed, and in a gas like the Sun, the higher the temperature, the faster the particles are moving. That's actually what it means for a gas to be at a higher temperature. It means they have more thermal energy. They're moving faster. So these protons are moving at super high speeds in the core of the Sun. And when two of them approach each other, they, of course, repel because they're repelled by the EM force. And they just bounce off like that. This is happening trillions of times per second in the core of the Sun. Now, two that are going particularly fast can get closer together before they zoom back apart from each other, right? And at any given moment in the core of the Sun, there are pairs of protons that are moving really, really fast so that they get close enough to feel that attractive, strong nuclear force and bond together. So this is why thermonuclear fusion occurs in the Sun and nowhere else in the solar system, because only there are the particles moving fast enough so that they can approach and feel that attractiveness of the strong nuclear force. So this is why thermonuclear fusion is driven by high temperatures, because these repelling protons have to get close enough in order to feel the attractiveness of that strong nuclear force. Now this is a graph showing the temperature structure inside the sun. So 0 is in the middle of the sun and 1 is at the surface. So as you see, as you go down from the surface, the temperature is fairly low at the surface, and as you go down it gets higher and higher. In the center of the sun, the temperature is something like 16 million Kelvin degrees. That's about 27 million Fahrenheit degrees. So it's super hot inside the sun. And so it's only in the core of the sun is that the temperature is high enough for thermonuclear fusion to be driven. And so this is why it's driven there. Now here this diagram shows some details of the proton-proton chain. This is the thermonuclear process that occurs inside the sun. So here at the top, see these two protons are bonding together because they're approaching at these super high speeds. And when this occurs, when they bind together, one of them immediately turns into a neutron. You know, when I was talking about radioactive decay, that protons and neutrons can switch back and forth into each other. And this immediately occurs after these two protons bond together. This composite particle now, a neutron bonded to a proton, can then encounter another proton and bond to it, giving you this, two protons and a neutron together. If two of these connect together, the bottom line of this chain of events is that 4 protons go away and 1 alpha particle is produced. An alpha particle is 2 protons, 2 neutrons. Same thing as a helium-4 nucleus. They just call it alpha particles for certain reasons. But this is the process that occurs in the core of the sun. And there's several ways we know that this is going on. One of them is that this particle right here that's released when the proton switches into a neutron, it's called a neutrino. It's just, it's symbolized here by a Greek letter nu, but it's one of the basic particles of nature. It's called a neutrino, and those things interact very weakly with other particles. They come straight out of the middle of the sun when they're produced. And this is an all-sky map of the neutrino brightness coming from outer space, and that bright spot in the map is the sun. So the neutrinos are coming from the sun. There's this huge neutrino detector in Japan called Super Kamiokande. It's deep underground. They fill it with water, but all of these gold-looking things are light-sensitive sensors that can detect very weak light flashes that occur when one of these neutrinos interacts with some of the water that's in one of these things. So this map of the neutrinos, they're neutrinos coming from the sun at exactly the rate expected if this thermonuclear process is occurring there. So now let me talk about the energy that's released. So you've probably seen this equation before, E equals mc squared. This is a mathematical equation that was discovered by Albert Einstein in about 1905. And what do these letters mean? Well, E stands for energy, M stands for mass, C is a constant, it's the speed of light. So speed of light's a real large number. Speed of light squared is a really large number. And so energy equals mass times the speed of light squared. What does that mean? Well, basically, mass and energy are sort of two versions of the same thing, almost like water and ice. And when an object has energy in it, it's a little bit heavier. So when literally when you heat up water on a stove, there's a mass equivalent to the energy, the thermal energy that you're putting into the water. It's a very tiny bit heavier. How much heavier is it? Well, not very much, because the equivalent mass is given by this equation. If you put a certain amount of energy in, the mass equivalent is that amount of energy divided by that super large number, the speed of light squared. People didn't realize this until the 20th century, that mass and energy are like two versions of the same thing, because the amount, if you heat up water on a stove, the amount of mass increase is extremely small, completely unmeasurable. It's only in these nuclear processes where a lot of energy is released that when that energy is released, the thing gets significantly lighter. Let me show you what I mean. The molar mass of hydrogen is 1.00794 grams. Remember, that's 1 mole of hydrogen atoms weighs that much. And the molar mass of helium is 4.002,602 grams. Now, you might think if 4 hydrogens come together to form 1 helium, then the molar mass of helium should be exactly 4 times the molar mass of hydrogen, but it's not quite 4 times. If I multiply the molar mass of hydrogen by 4, I get 4.0317. You see, that's a little bit more than the molar mass of helium. Why is that? Because when the helium is formed, the sum of the mass comes out as energy because it's an exothermic process. So you see, you weigh 4 moles of hydrogen, you get 4.0317 grams. You weigh 1 mole, the product of those 4 moles is 1 mole of helium. You weigh that, it's a little bit less than that. The difference is about 0.73% of the original mass. So when 4 protons come together to form a helium nucleus, about 0.7% of the mass is released as energy. Now that may not seem like much, but that's a whole lot of energy. When you multiply that amount of mass by the speed of light squared, you get 2.6 trillion joules. So 4 grams of hydrogen forming 4 grams of helium releases 2.6 trillion joules of energy. That's a very, very large amount of energy. That's way, way more than the energy that's released when 4 grams of gasoline burns in the energy of your car. In fact, it's about 45 million times more. So this is a very, very exothermic process. And the fact that it's so exothermic, the fact that so much energy is released, this is why the sun has been able to shine so brightly for so long. It's been burning brightly for 4.5 billion years, because the fuel, or the fuel that where its energy comes from is so stuffed with energy. Okay, this is another thermonuclear process that occurs in heavier stars. The bottom line is the same. Protons are converted into helium nuclei, but carbon nuclei, oxygen nuclei, and nitrogen nuclei are involved in it. It's called the CNO cycle. The bottom line is the same as the proton-proton chain. I'm just showing you this because there's other nuclear processes that occur in other stars. Now, when the sun gets old, its core temperature will actually rise, and at higher temperatures, more thermonuclear processes can occur. So here you see 3 helium nuclei can come together to form a single carbon nucleus. This is called the triple alpha process, because another name for a helium nucleus is an alpha particle. And this is thought to occur in the late stages of a star's life. Carbon is the 4th most abundant element behind hydrogen, helium, and oxygen, because this process occurs in large rates in the late stages of stars. So here's another thermonuclear process that can occur. And at even higher temperatures, more thermonuclear fusion can occur. Here you see processes going all the way up to iron nuclei, iron 56, with 56 nuclear particles. These processes mostly occur in very heavy stars, stars that are heavier than about 8 times the mass of the sun. And so they produce these very large quantities of heavy elements. And this is the cross-section of what it's thought the composition of the inside of one of these high-mass stars is like right at the end of its life. So there's a core of iron surrounded by silicon, surrounded by oxygen, surrounded by carbon, surrounded by helium, surrounded by hydrogen. So these are the elements thought to be produced in very large quantities toward the end of the life of one of these very heavy stars. This isn't all the elements that are produced, the ones that are produced in really large quantities. Now, what happens at the end of the life of these stars is with that iron core builds up to a certain quantity, and then for reasons that have to do with other physics, it collapses and the star explodes. And this is called a core collapse supernova. And these are seen all over the universe. So here, this is an image of a very distant galaxy. It's billions of stars, but the fact that it looks like a little smudge of light is because it's extremely distant. And here it is at some point later in time. That flash of light that's occurring, that is a core collapse supernova. And these things remain luminous for a couple of months, and they're seen all over the universe, but they're mostly seen at large distances because they only occur in ordinary galaxies like ours about once every century. So that if you look far enough away, you're looking at billions of galaxies, so they're actually observed fairly often. Here's another galaxy, very distant, and at some point a supernova was observed there. Here's a third galaxy, very distant, and another supernova. So these supernovae, these core collapse supernova, when they go off, those elements that were produced by thermonuclear fusion are blown off into space. And there's even more thermonuclear processes that occur during the explosion. And this is actually where we get most of the elements of the periodic table. Here's a periodic table that is color-coded for what is presently thought to be the origin of the various elements. And you can see exploding massive stars. That means exploding high-mass stars is the green. And that's the bulk of the stuff that we have in the solar system. Comes from that. There's a couple other sources in here. Exploding white dwarfs. A white dwarf is another kind of, it's a burnt-out star, but they can also explode. They're thought to be responsible for some of these elements. And then when a low-mass star dies, a star like the sun, it can actually produce elements of the heavier elements of the lower half of the periodic table. And then very recently, it was discovered that when two neutron stars merge together, they can also make those heavy elements. A neutron star is the remnant after the end of a high-mass star. When it explodes, one of the possible remnants it can leave is a neutron star. One of these was observed a couple of years ago, and it indeed cranked out some heavy elements. So you see the periodic table of elements. All of them come from these processes, mostly associated with stars. And so that's one of the significant things about thermonuclear fusion, is that's where we get the elements of the solar system. And here's a chart showing the relative quantities of the various elements in the solar system. So horizontal axis is size of the nucleus, and vertical axis is abundance in the solar system. And you can see hydrogen is the most abundant, and then helium, then oxygen, then carbon, then neon, then I think iron is the next one behind that. So all these highly abundant elements in the solar system, those are high in abundance because they're produced in large quantities in thermonuclear fusion. Now, the core of the sun has these super high temperatures, and that is why thermonuclear fusion can occur there, right? Is it possible to do this on Earth? Since it's so energetic, it cranks out so much energy, wouldn't it be nice to be able to do this process in reactors on Earth to make a lot of energy, right? I mean, we use mostly fossil fuels to make power and to run our cars and everything, but that's chemical energy, that's a chemical process, and we're eventually going to run out of that stuff. So wouldn't it be nice to be able to do thermonuclear fusion on the ground? The problem is it takes this super high temperature, even at the core temperature in the middle of the sun, 27 million Fahrenheit. The rate at which thermonuclear fusion is occurring there is extremely low. So we'd have to achieve even much higher temperatures than this. And how do you do that? How do you heat protons up to billions of degrees and contain it and to get the energy out of it? It's very difficult to do. The one form of thermonuclear fusion that people have managed to do is in nuclear weapons. So you know that nuclear weapons were invented in World War II by the U.S. military, and the process that occurs in nuclear weapons is nuclear fission, which is the splitting of heavy atoms. That doesn't take super high temperatures. You can do that at room temperature, like what's done in nuclear power plants on Earth. So the first nuclear weapons use nuclear fission because it's easier to make it occur. But if you put a fission bomb in a device with some material that can undergo fusion, a fission bomb, of course, produces extremely high temperatures, billions of degrees, and that can cause the thermonuclear fusion of this other stuff. So you see the red material in here, it's labeled fusion fuel. This is the stuff that undergoes fusion. And that's a mixture of deuterium and lithium. Deuterium is the nuclei, it's one of the isotopes of hydrogen. It's a proton bonded to a neutron is what the nucleus is. And lithium is element number 3, right? 3 protons and either 3 or 4 neutrons. Those can react together to form helium nuclei, and a lot of energy is released. So it's not quite the same reaction that occurs inside the sun, but it's thermonuclear fusion. And here is a thermonuclear explosion. This is in the 1950s. This was developed by the US and by the Soviet Union. And this is one of the test blasts. So that's many miles away. That's the mushroom cloud from one of these thermonuclear explosions. I think this is a test by the United States. So thermonuclear fusion has been mastered by mankind, but not for a very productive purpose. It's been mastered for the production of extremely powerful weapons, but not for power production as of yet. Okay, so here's a few things about thermonuclear fusion.